Hello, everybody. Today we will continue our lecture on fugacity and fugacity coefficient. This time we will also tackle the fugacity of species in solutions. But before we proceed, let me quickly give a recap of what we did last video, which is to solve this example. We calculated the fugacity and the fugacity coefficient using the steam table, and I just thought of a nice analogy for to explain what is fugacity. So the analogy is that imagine that real gases are wolves in sheep's clothing. They pretend to be ideal gases, and as they pretend, the pressure, uh, their pressure is the fugacity, while the ideal gas would be the its pressure would be the given pressure. So as the real gas pretend to be ideal gases, the representative pressure is the fugacity. So I hope that helped you imagine what is fugacity. So because it's an abstract concept and I'm trying to find an easy explanation. Anyway, imagine that real gases are wolves in sheep's clothing. So we also plotted this graph. I did not um, explain the graph further, like what does this imply, the slope of each line imply, because that's going to be part of your homework. Uh, but for your homework, just notice, um, compare this line right here, this dashed line, which is the what if the fugacity what if this line is the ideal gas wherein the fugacity is equal to the representative or the given pressure, compared that with the fugacity of the real gas. So as you can see, how do they compare when the pressure is low and the pressure is high, and also observe, okay, what happens to the slope when the pressure reaches the P saturation, and also do that for the fugacity coefficient as well. Okay, so that is part of your assignment. I won't discuss that. Now we move on to the next lecture. So now we put our attention on the fugacity of a species in solution. It's actually parallel, okay, on how we define fugacity of a pure species. So remember, we have this equation for fugacity on the Gibbs free energy, and for ideal gas, it's equal to the integration constant plus RT ln the partial pressure of the real gas. The ideal gas. So that's for ideal gas. This one is partial pressure. For a real gas, it's the same equation, but this time we replace the partial pressure of the inside the natural log with the fugacity. So in parallel, if we're talking about the partial molar Gibbs free energy, which is the chemical potential, so we now put a bar sign here, and this time the fugacity is represented by the Fi hat, where Fi hat is the fugacity of species in solution. It does not make it a partial molar property, but it just the hat here means that the species is in solution, not in not as a pure species. Okay? For to describe the equilibrium, we have a general criterion, okay, wherein, for example, we have multiple phases, alpha, beta, etc. So Fi hat for alpha is equal to Fi hat for beta, and so on and so forth, when they are in equilibrium. So multiple phases at the same temperature and pressure are in equilibrium. So take note that we're talking about the condition of same temperature and pressure when the fugacity of each constituent species is the same is the same in all of the phases. And this criteria of equilibrium is most often applied in the solution of phase equilibrium problems. Okay. And next, we recall the definition of residual property. So remember, it's the difference between the real property and the ideal gas property. Okay. And of course, this holds true that it should be the same at the same temperature and pressure. Multiplying this equation with the number of moles, we get the expression here. And then when we differentiate with respect to the number of moles of species I at constant pressure, temperature, and um, number of moles of all the other species except for I, that is n sub j. Okay, so differentiating it would give us these expressions. And then remember that we can also express the residual property. Okay, so as a as a similar equation, okay, for the partial molar property. Okay, so simply just express this one as a partial molar property. So this gives the general expression for partial residual property. Okay, so I hope that you notice the difference that we simply express the residual property in the form of a partial molar property. So we have this bar right here. And then being more specific, we focus on the Gibbs free energy as the property. So this is the partial molar Gibbs free energy of partial molar residual. Okay, residual gives free energy. So that is this expression right here. By the way, the sign right here is just means we defined it. Okay, so it's not an equal sign. We defined it as this way. And then using the three equations, so we have initially this equation, okay, and also um, for ideal gas, that's going to be the partial pressure. So mole fraction I times the total pressure is the partial pressure, okay? And then for a real gas, that's going to be Fi hat, which is the fugacity hat, okay? Um, so again, the hat means the species is in solution. So now we have an expression for the partial molar gives free energy for the ideal gas and the partial molar gives free energy for the real gas. We can substitute it to our equation for the partial molar residual gives free energy. So we substitute equation F and R into equation S, and so the integration constant is removed, and we're left with this equation. And because of the property of natural log, now this difference here becomes just a ratio of Fi hat over the partial pressure. Okay, and if you will remember, um, this expression is actually the fugacity coefficient, Fi over the partial pressure. Fi over Pi is the fugacity coefficient, but since we're in solution, okay, we're talking about the species in solution, it's going to be phi hat. Okay, phi hat. So now we have an expression for the partial molar residual Gibbs free energy in terms of the fugacity coefficient in for species in solution. So it can be applied to gases and it may also be used for liquids. We simply need to replace the mole fraction y with x sub I, which is our convention for the mole fraction in liquid phase. All right. Okay, so some important notes. Remember that for an ideal gas, the just like our pure species, the fugacity of an ideal gas is just equal to the partial pressure of the gas. So this time the fugacity of an ideal gas for a species in solution, okay, so may hat is equal to its partial pressure. So it's the same concept. And then also for an ideal gas, the fugacity coefficient of the species in solution is just equal to 1. And for an ideal gas, of course, the residual property is 0 because there's no difference between this term and this term, so the residual property is 0. So just an important note for the ideal gas mixture. Now we move on to the fundamental residual property relation. So I hope you still remember this equation right here. Um, in your ChE 142, the equation stops at this term, but that is for pure species of a which means it has a single composition. Okay. To make it more general, okay. So remember in your ChE 142, we used the Gibbs free energy as a generating function and we obtained this equation. But that one is for uh, a single species. To make it more general, just like how we derive the generating function for a multi-component system. So we add this term right here, and this is for a homogeneous single phase of changing composition. So it's for an open system. So it's a generalized form. Okay. Now, in terms of residual property, a similar equation can be written. Okay, so we want to express this one as a residual, so we make everything a residual property, and now this is the fundamental residual property relation. Where, okay, where this term, okay, the partial molar residual gives free energy over RT is actually the natural log of phi hat from the previous slide. Okay, so just transfer RT to the denominator of the left hand side of the equation. So this is the same equation as before. So we can replace this one. Okay, where our phi hat is equal to the Fi hat over the partial pressure. Okay. So just transform this equation to this one because we already derive an expression for this term right here. So we end up with this equation. And then, so in your CHE 142, if you will remember, we already know how to get these values. Uh, for example, in generalized correlation. So, for example, if we have a constant temperature, so we're left with these two expressions right here. If we have a constant pressure, then the left-hand side equation will just be equal to this one, and we know already how to get this value. So if we have now a constant pressure and temperature and also constant composition for all the species except for I, then we're left with this expression and the last term. So this is going to be that um This is going to be the ln of phi hat equal to the quantity right here. And this equation demonstrates that the logarithm of the fugacity coefficient of a species in solution is a partial property. Okay, this is a partial property with respect to the residual Gibbs free energy over RT. Okay. So right now I know that I'm just feeding you a bunch of equations, but I do hope that during the example we will all appreciate this better. Okay. So just bear with me for feeding you a bunch of equations. All right. We also have so why are we doing this, by the way? Let's go back to the big picture here. It's because we want to get an equation for the fugacity coefficient. Okay. That's why we are deriving all of these equations. Again, the fugacity's coefficient is important to us because fugacity in general is important to us because it would help us describe non-ideal behavior. It's a criteria for equilibrium, and because it's related to chemical potential, it gives us it helps describe the direction of the spontaneity. Okay, so we end up with an equation for the Fugacity coefficient, and there are other ways we can calculate for the Fugacity coefficients using the equation of states. Particularly, in this slide, um, I'm showing you three cubic equations of state: Van der Waals, Redlich-Kwong, and Peng-Robinson equation of state. So if you will remember, we have equations for each of these equation of state for pure species I. Okay, so there you have it on the first row for each group. And then um, the fugacity coefficient for species 1 in a binary mixture is also shown here. It was derived separately. Okay, and also species I in a mixture. So this one is the generalized um, equation for species I in a mixture. Okay? Okay, so there are the ways we can calculate for the fugacity coefficient. So more ways, now going to show you more ways to calculate for the fugacity coefficient. So it's just like if you will remember compressibility factor in your ChE 142, there are different approaches in order to calculate for the compressibility factor. So the same way we're doing that for the fugacity coefficient, right? The next approach would be using the Kessler correlation, which I think you're familiar with this because of the compressibility factor in ChE 142. So for this correlation, we're given a, a parallel equation. So before, if you remember, this is for compressibility factor z naught plus the eccentric factor multiplied by z raised to z1. Okay, not raised to 1, but z1. So the same way we can express phi using the Lee Kessler correlation, he made those persons made a parallel equation for fugacity coefficient. And because this is natural log, we just take the exponential of both sides and we end up with this equation. And just like in compressibility factor, um, we can use the tables. Okay, we can use the table. So let me share the tables. Hold on, please. Okay, these are the Lee Kessler tables for phi naught and phi 1. Okay, also from Smith and Van Ness. So we can use a table to read the value for phi I naught and phi I 1. but we just like in compressibility factor, we need to read them using the reduced pressure and temperature. So again, where will you get the how will you get the reduced pressure and temperature? Just divide the given pressure and temperature with the critical pressure and temperature, and the critical values you get from uh, Appendix B, okay, which is this one, by pure species. So for each species, you can get the critical temperature and pressure, and also the eccentric factor. Okay, so I hope you still remember how to do that. All right, so this is a screenshot of um, the Kessler correlation tables. The next approach in calculating, okay, the fee. Oh, so by the way, an important before we move on for this one, for the first approach, the Lee Kessler correlation, we're under the generalized correlation. Okay, this is applicable for pure species. So please take note of that. This condition must be true. And then for pure gases, we can also use the generalized correlation from the virial equation. So I hope you still remember, I think we derived this before from equation K. Let me just briefly, yep, this one. Okay, so when we first defined fugacity, okay, we derive already equation K. Okay, so we can use the generalized correlation from virial equation because this quantity right here, z minus 1, in for the virial equation, it's Bp over RT. B describes is a quantity that describes the interaction between the molecules. So um, if we replace that into the equation and then in terms of reduced temperature and pressure, okay, so we substitute T and P with TR in terms of T of reduced temperature and pressure. So we're able to get an expression like this. Okay, so we end up with this expression. So I hope you still remember your equations from the virial equation, from the generalized virial equation. Okay, so now we can get an expression for phi, okay, with the reduced pressure, temperature, and also the virial equation constants, B naught and B1. Okay, so where B naught is equal to this equation, okay, and so it's not a constant, rather it's a parameter wherein you calculate it using PR. Okay, so B naught and B1 can be calculated. So again, we have an equation for the fugacity coefficient. Um, and this time, this is still for pure species. So what about species in a mixture, specifically in a gas mixture? Okay, the third approach is still using the virial equation, the truncated virial equation. Say, so we have this, if you will remember, this is our virial equation, and B, as I mentioned, is the uh, interaction between molecules. So if we have two molecules, I and J, B sub ij is the interaction between them. So to get B, we have to sum all of these interactions. Okay, so this equation just takes the sum of all of the interactions between two molecules. Okay, where I and J is our species in a gas mixture. So multiplying the mole fraction of each species with their interaction and summing all the interaction, you get the constant B. So for the special case of a binary mixture, we can expand this summation into this one. Okay, so just expanding that. And then since B sub 1, 2 is just equal to B sub 2, 1, so we simplified uh, the expansion into this one. So just combine the two. All right. And then going back to our equation before, so we made a parallel equation this time. Since we're talking about species in solution, so our Fogassic coefficient is represented with phi hat, which means species I in solution, and our compressibility factor is the partial molar compressibility factor. Okay. So Z bar is the partial molar compressibility factor as uh, expressed in this equation right here, taking with respect to the species I, taking temperature, pressure, and the number of moles of other species constant. Okay. And this is equal to 1 plus, so this value. Okay, so where did we get this? So remember, z minus 1 is equal to, alright, so this one, z is equal to 1 plus b PRT. So just simply expressing this equation in terms of partial molar property. So if we want to express that in partial molar property, then therefore our B should also be expressed as a partial molar property. So um, the next equation just gives an evaluation of this one. By the way, sigma 1, 2 is actually, so it was not shown, but it's this one. So we just let a variable be equal to, okay, this expression right here. And it's just simply taking the partial derivative of b with respect to n sub I, or in a binary mixture n sub 1. Okay. Next, we substitute that back into our equation, and then so we substitute back into our equation uh, that one to here. Okay. And now we get an expression for the Fogassic coefficient for species in solution, both for species 1 and 2 for a binary mixture, where sigma 1, 2, okay, so is equal to this equation right here. Alright. In general, if we have a solution that has more than two species, this will be the equation that is applicable. Okay, so this one is just applicable for a binary solution. So a mixture of um if we have a mixture, so this is the general equation that we're going to use. Okay, so just take note of the specific equation for sigma. Okay, so here B sub kk and BII, of course, they are pure species because the same um, species I or same species 2. So the interaction between two species I and J would mean B sub ij is the molecular interaction between two different species. Okay? And take note, please, that the equation for Bij, okay, is this one. So it's like the imperial equation for B sub ij, and where B not, and B1 are evaluated similarly to that of a pure component. Okay. So what do we have any other um, values that we need to compute? Okay, let me check. So we also have an equation for the eccentric factor between two species because before our eccentric factor is just for one species, but if we have two species, as you can see, it's just an average of the eccentric factor of the two species. And then we also have an expression for to calculate the critical pressure of two species and also the critical temperature for two species and the Z and the V. So anyway, these equations will be demonstrated later in an example. So I hope that you will appreciate this more once we demonstrate this in the following examples. But again, going back to the big picture, our goal is to calculate or to have an expression for the fugacity coefficient. And we have um, expressions using residual property relation. We also have an equations and expressions for using the equation of state. And next we have equations using generalized correlations for pure species, for uh for still pure species, and then also species in a mixture. Okay, so for species in a mixture, phi is represented by phi hat. For pure species, it's just phi. So that's the important essence of this lecture. Okay, just that we have different approaches in getting phi and or phi hat. Okay. Alright, so this wraps up the lesson for on the fugacity and fugacity coefficient. Our next video will have a demonstration of these equations in two examples. So I will end the video for now.